Hi friends, welcome to the part 15. This is the last video of this series. In this video I am going to talk about integer multiplications in computers at a very high level, just to give you a sense of what is involved. Link to the previous video is in the top right corner. Here we are going to talk about first binary representation, multiplication of small numbers in computers, and multiplication of big numbers. And during the course of talking about big numbers, we will talk about algorithms, order of algorithm, and brief history of multiplication algorithms. So let us start with binary representation. So on one side we have decimal and the other we have binary number. So let's take the example of 48. Let's take one more example of 673. So in decimal we have base of 10 over here, and the numbers are going to be between 0 and 9 at each place value. So in binary we have base as 2, and at different place value we will have numbers between 0 and 1. So let's do some examples here as well. Now let's talk about multiplication and left shift. So suppose we have to multiply 12 and 10 in the decimal system. So we get 120 as an answer. So here we shift 12 by one place to the left. And suppose if we have to multiply 12 and 11, then we will shift 12 by one place to the left, and then we will add 12 to it. Similarly, if we have to multiply 12 and 101, then we will shift 12 by two places and then we will add 12 to it. So the thing is, if the multiplier has only ones and zeros, then shift and add is enough to get the answer of the multiplication. And in binary system we have only zeros and ones. So the multiplier will always have only zeros or ones. So let's do some examples. So since in binary system all the numbers are zeros and ones, so to multiply two binary numbers we only need to shift and add. Multiplication of small numbers in computers. So we will talk about three techniques: peasant technique, shift and add, and quarter square technique. So let's start with peasant technique. In peasant technique, when we have to multiply two numbers, we half one number at each step and we double the second number in the same step, and then we ignore the steps where the number that we had halved is an even number, and we only add the odd parts and to get the answer. Like for 23 and 5, we halved 5 and we get 2, and then we doubled 23, so we got 46. Then we halved 2, it became 1, and then we doubled 46, it became 92. So then we are going to ignore the even number step, then we will add numbers at rest of the steps. So here we get 115. Same way we can repeat in binary system. and we get the same answer. So in shift and add, we start with 0. So at each step we shift left, then for 1 we add, and if it is 0 then we skip adding and we move to the next number. So let's see this in this example. So we start with 0, then for this one we add it and then we shift it. Now then we again get 1, so we add this number here and then we shift this number, so we have one more 0 here. And the same thing we do at the next one. We add this number over here and then we shift it by one more place, and then we add all the numbers that we had put over here, so we get this. Let's do one more example. So shift left at each step, add at 1 and skip at 0. So we start with 0. Then since it is 0, we only shift it by one place. So 1 1 and then 3 zeros. Then we get 1, so we add this and then we shift it by one more place to the left. So one more 0 gets added here. And so we repeat. So and the next one is 0, so we just shift this number by one more place to the left, so we add one more 0 here. And then the next number is 1, so we add this number here. So when we add, so it is just a peasant technique in a different form, because here also we only add the odd parts and we skip the even part. Now let's talk about quarter square technique. So it is based upon the fact that x times y is same as x plus y whole square minus x minus y whole square divided by 4. So we keep a table of n square by 4. And for x and y, we take n1 as x plus y and n2 as x minus y. So let's do an example. So x plus y is 27 and x minus y is 3. So we subtract these two by reading from the table and we get the answer. Now let's talk about multiplication of big numbers. So here first we will learn about algorithm. So what is an algorithm? So algorithm is a finite sequence of computer implementable instructions. It consumes space and time. Order of algorithm. So it defines how space and time change with respect to the size of the input. So the order of the algorithm can be constant or logarithmic or linear, polynomial or exponential. Now let's talk about brief history of multiplication techniques. Prior to 1962, it was order of n square, which was implemented using shift and add. So question is, what started the breakthrough? So the answer is the uni-solvence theorem. So basically it says that polynomial of order n is uniquely determined by its n plus 1 distinct points. If we have ax and bx as two polynomials of order n, then cx will be of order 2n. So if we pick 2n plus 1 points on each polynomial a and b, if we multiply them individually and then we interpolate points back to the polynomial, then we will get the polynomial cx. So instead of doing n square multiplications, now we have to just multiply 2n plus 1 points and then we have to interpolate it back to the polynomial. So let's see how it is done. So this was first done by carryover in 1962. So if a and b are two n-digit numbers, we split them into two parts recursively. At the lowest level, it represents numbers as polynomial of order 1. So like this, so two numbers will get represented like a and b polynomial. So if we multiply ax and bx to get cx, we will have something like this. Then we will evaluate it at 3 points, 0, 1 and infinity. To evaluate at infinity, we will divide the polynomial by the highest power of x. So let's do an example. So numbers will be split recursively. So in the middle here you see, if we will do cross multiplication over here, we will have 2 multiplication. Instead of that, there is only 1 multiplication and 2 subtractions. So it saved 1 multiplication out of every 4 multiplication. So how big is this improvement? If you multiply two 1024 digit numbers, this approach will take 59,049 single digit multiplications, whereas traditional technique will take 1,048,576 single digit multiplications. Then in 1963, Tom Cook generalized it to larger degree of polynomials. So for k equal to 1, it becomes a traditional long multiplication technique. For k equal to 2, it becomes carryover-free technique. For k equal to 3, it becomes Tom 3 technique. And this has the order of n raised to the power log 5 divided by log 3 or log 5 base 3, or in a generalized form it has the order of n raised to the power log 2k minus 1 base k. So let's do an example of k is equal to 3 where the polynomial order is 2. So numbers can be expressed as a0 plus a1x plus a2x square, and similarly for b. So if you multiply ax and bx for cx, then you get this. So here we have to evaluate it at 5 points: 0, 1, minus 1, minus 2 and infinity. So how do we do that? We write it in matrix form. Then you have to do point-wise multiplication to get C0, C1, C minus 1, C minus 2 and C infinity. Then we have to interpolate it back to get the coefficients. So this is the inverse matrix for the order 4 polynomial that converts from coefficients to polynomial value. So let's do an example. So if we have to multiply 10,234 with 50,678, we are going to split it at 3, 4, 0, 2 and 1 for A, and 7, 8, 0, 6 and 5 for B. So A0 becomes 34, A1 becomes 2 and A2 becomes 1, the coefficient of polynomial A, and the coefficient of polynomial B, B0 becomes 78, B1 becomes 6 and B2 becomes 5. So now we calculate value of polynomial A at 0, 1, minus 1, minus 2 and infinity. So from this coefficient, how do we get the answer? So this 5 is C4. So and for each we have 2 zeros. So we will add 8 zeros in front of 5. Then for 16 we will add 6 zeros in front of it. For C2 260 we will add 4 zeros. Similarly for 360 we will add 2 zeros, and then we will add this 2652, and if we add them together we get the answer. So this completes the video and this series. I hope you liked it. Please share your comments, thoughts and other topics that you would like to see videos on. Thanks for watching. Please subscribe to my channel if you have not done so already, and please hit the like button and bell icon. Enjoy.